we are trying to now get to compute Green's function with perturbations. Okay. Now, perturbation could be, so what could be perturbation? You can easily think the free electron field, but now you put in electromagnetic field. So, electron will interact with the electromagnetic field. Okay. So, that is a perturbation, or we can think of electron in a magnetic field, okay, or electron in a with some which is called some impurities in condensed matter physics, okay, or electron interacting with itself, and that interaction will become a potential. Okay. Of course, we will not do lot of it, this is not the course on detailed calculation as I said, but this is how we bring in interactions, okay, and then the effects will come out in the Green's function, energy eigenvalues, corrections. So, we can derive all that in that. Okay. All right. So, let us look at some more ideas on the Green's function. Again, we will keep it simple for time being, bring in relativity. Okay. So, that is what is, I am not going to do Dirac equation, but we will stick to Klein-Gordon equation, but the idea will become explicitly clear in this discussion. So, we start with the Klein-Gordon equation, okay, which I have done in the past, but let me in fact try to derive the Klein-Gordon equation. So, this is the Einstein equation, no? Everybody knows about this one. I made C equal to 1, okay, E square equal P square C square plus MC square squared, okay, but so this is called E and P are 4 momentum energy, and 3 component of momentum becomes 4 vector. Okay. Now, one thing you can see, in fact, it was noticed by Schrodinger, Dirac, and I am sure some other people, that energy square root becomes plus minus square root. Energy takes positive and negative values both. Now, we are all used to positive energy, no? I mean, in classical physics, energy is always positive, but in quantum mechanics, energy can be negative. We have energy bound states where energy is negative. So, for free particle, this is the free particle. For free particle, what is energy, negative energy state, what does it mean? And you can easily see there are problems. I am going to show you in just couple of slides that negative energy states or negative energy particles will have negative probability, negative mod psi square, okay, and that is a problem. So, there are ways to overcome it by bringing in antiparticle, which some of it we discussed for many body problems. We say, well, we will bring in holes. Negative particles, negative energy particles are basically antiparticles. We discussed it, no, I mean that was done some time back, but in relativistic field theory we will bring in antiparticles today. Okay, so now we know that energy will bring in again make these operators. In fact, this was first supposedly written by Schrodinger. This equation which I am going to, Klein-Gordon equation is called, but written by Schrodinger. So, energy operator is I h bar d by dt, and momentum operator is I h bar grad. I h bar or minus I h bar? Minus I h bar. Okay, so substitute it here in this equation. The way we write down, how do we derive Schrodinger equation? Energy is P squared by 2m plus V, right. So, we derive Schrodinger equation, but we do it for relativistic thing now. So, we put energy operator as d by dt, partial d by dt, and this is minus I h bar grad. Substitute it here, and now I can do the derivation, but I will just leave it for you to just figure it out. This is what you will get the equation. Okay, this is just simple algebra, and this is correct, I checked. So, in fact, let me just do it. So, I h bar d by dt, so h bar is 1, no? So h bar we do not carry around. So, E squared will be minus this, right, and this one equal to square of this will become minus Laplacian plus m squared will remain m squared. I will 2I will give you minus. So, when I take this to the right hand side and bring this to the left hand side, I will get this. Okay. So, with m equal to 0 we get the free waves, which is a photon. M equal to 0, mass of the photon is 0, but there are particles with non-zero mass. pions, mesons, there are a lot of particles with non-zero mass, and this is the equation for those particles. Now, this is historically, I am not 100, well basically I am not a historian, but this was written by Schrodinger himself, and then is attributed to Klein and Gordon, these two people. So, this is the equation for with H bar included, this is the equation for relativistic particles. This has a problem called locality problem, and to overcome it Dirac wrote the Dirac equation. So, this is second order in time, right, and second order in time leads to some problems which I will not discuss. So, to overcome it Dirac wrote the first order equation. Dirac equation is the first order in time, but then you have to bring in the spin matrices, right, spin order you have to bring in. So, that is a known complication, and the algebra is reasonably complicated. So, stick to this and we will try to do quantum field theory for Dirac equation, for Klein-Gordon equation. Okay. So, this is the equation. So, it has all sorts of solution if you bring in negative energy E. So, I am going to try the solution e to the power I k dot r minus I e t. K is momentum, h bar k is momentum. So, that is a very nice thing in relativity. Momentum is just h bar k and energy is h bar omega. So, omega and k, omega k vector form a 4 vector, right, 4 relativistic vectors, as here energy and momentum also forms a 4 vector. Classically this is what we do, but in quantum mechanics we bring in this and we can deal with particles. Now, we write down waves like this. In 1D this corresponds to e to the power I kx minus omega t bracket. Omega is always positive and it comes with a negative sign, right. We don't consider negative frequency. Energy is always positive in classical physics. We change the sign of k. K positive, the wave will be going to the right, right. X is changing, x is increasing and t is increasing both. So, that is the wave going to the right. It is a positive momentum wave, and if k is negative, then wave will go to the left. If t increases, x decreases. Okay. Now, what if we have omega negative? That is a problem. In fact, Feynman thought about this, and there are two people which I am going to give the name. He thought before Feynman, I forget the name. Okay. So, they constructed ways to interpret this negative energy particles, how they move in space time, and I will just show you hand waving way to show that this negative energy particles will go backward in time. Okay, I will show you how you can deal with negative energy states in field theory. Okay, so this is this slide about. So, omega can be both positive and negative. This was a nice observation. So, we keep it like this, omega positive, and I just interpreted this, but omega negative, that means okay. So, omega negative, this becomes e to the power I k dot x plus I omega t. Okay, that is the argument, and interpretation of it becomes a problem. Okay. So, let us see how to interpret this. By the way, you will have to deal with both particles and antiparticles at the same time. So, you can't say that I will deal with particle first or antiparticle later. You have to write down for all these particles and antiparticles simultaneously, and there must be a way to do it. Okay. Now, so let us look at the current, assuming both positive and negative energy states are possible. So, this J psi, no, I derived this before. So, the J0 is a density and J vector, 3 components are the probability currents. We did for Noether theorems when I was deriving it, I derived J mu, and del mu J mu is conserved, we did all that. So, J0 is this. J0 is supposed to be the mod psi square, probability density rho. Now, I substitute this one, okay. E can be negative, please remember, E can be negative. Substitute it here, what will I get? I psi star will give me okay, the I will become minus I, but d by dt will be so psi star d by dt will give me I minus IE, correct. This will come here and psi, that is the first term. Second term minus psi d by dt of psi star, and psi star is what? N e to power minus I p dot x minus I t. So, this will be plus E, right, plus I psi star. So, when I take the derivative I will get plus I. So, minus and I squared will give you minus 1. So, this becomes E times mod psi square, and here also I will get I squared is minus 1. So, 2 E mod psi square. This is supposed to be the probability density, okay. So, there are particles and this is the probability density of the particle in the quantum probability density. Now, E is negative, then what happens to rho? Mod psi square is positive. So, if E is negative, then rho becomes negative for negative energy states, and that is a problem, and that is the reason why supposedly Schrodinger abandoned this whole equation, says this is not physically possible equation, okay. But there is a way to overcome this, and there is a way to make a formalism, and that is what I will come next. So, this Stuckelberg, okay, Stuckelberg interpretation. So, the idea is quite nice. So, electron, and this is the nuclei, electron is going forward and going to hit the nuclei, okay. It is going to slow down if it is same charge in negative, or okay, depends on what is the sign of n. So, it is moving towards that direction. So, imagine that this is negatively charged. So, well, nuclei is normally positively charged, no. So, it will accelerate right now, okay. It will accelerate, positive charge means it will accelerate. Now, let us imagine that we turn this the movie, I record a movie, but where the electron is moving forward, but now I turn the movie, play it backward. I am just going to play the movie backward. So, what will happen? So, electron which is accelerating will go in the, so it here, so by the way, electron is time t equal to 0 is here, t final is here, okay. It has slowed down, but if I play the movie backward, then what will happen? Electron will go backward and will accelerate, right, correct. My nuclei is, I assume that nuclei sits there, no problem, it does not, I have clamped it, or it is too heavy, it does not move. So, how is it possible? So, well, if I want to make a physical interpretation of this, then I say that this particle is a positively charged, okay, and is going with opposite momentum, okay. So, this is what is interpretation of this charged particle. So, this is a positron with positive charge, and it is going with the opposite momentum, okay, and its energy is also, if you think of particle, then it is a negative energy state, but if you think of positron, it is a positive energy state. It is very similar to what we did for hole. If you think of hole, then it is positive energy, but if you think of electron, then it is a negative energy state. So, to deal with positron, we say that it is an electron which is moving backward in time, okay. So, this is how it is dealt, and so the wave function for this particle is this, okay. So, we can now deal with both positrons and electrons in interactions. So, I am going to write down in fact the operators for antiparticles similar to what we did for holes, and then I can do all the field theory, okay. So, with positive E, this antiparticle, Of course, you can break your head with this interpretation. In fact, it is very interesting interpretation and very important interpretation. So, let me just give you a brief. I am not sure how many of you know about this, but in classical physics parity is conserved, right? You know this. What is parity conservation? So, if you have some experiment where I see some well, there are certain spins which are happening, some particles are spinning or some helicity is there, and I do the experiment, okay, but these particles involve certain spins, okay. So, this has a helicity, right, spinning is always helicity. If particle moves in that direction and spinning, then you can compute spin dot velocity, it will be a pseudo scalar, okay, and this guy must be present, pseudo scalar. So, classically you may think that if I do the experiment in a mirror, then velocity will flip, but spin will not flip, okay, and it turns out you say that classically you can perform an experiment where this helicity will be opposite, but that is fully realizable. That is what one would think classically, but it turns out in quantum world parity is violated. That means this kind of quantity is non, well, basically you may think that some experiment will be positive, some experiment will be negative, right, if its parity is conserved, but it turns out your Hamiltonian has this kind of quantities, okay. I will not get deeper into this, but you can just read about parity violation. Okay, and this won the Nobel Prize for C. N. Yang and T. D. Lee, and there is a person who did experiment, Wu. She did not get the Nobel Prize, but unfortunately, but anyway, this is the experiment. Okay, it turns out this parity is connected with charge conservation, charge conjugation, sorry, charge switch and time reversal. So, I am telling you that going backward in time, right, and charge. So, three things are related: parity, time and charge. You can see here I was trying to go backward in time, that is time reversal, and charge, right, you can see that here. So, CT I talked about, but you can also think of something spinning, then parity will also come. So, it turns out these three are not conserved individually. Parity is violated, time reversal is violated and charge conservation is violated, but CPT together is not violated together. Okay. So, this is a CPT conservation law. It is a discrete symmetry, but it is conserved. Okay. Anyway, so that is not our objective for this course, but it is an important thing for antiparticles, parity and time reversal. Anyway, so let us look at how to do field theory for this. So, I construct this field operator phi. So, phi is a wave function, okay, but it is an operator. Well, I should not say wave. For wave function I construct an operator phi. So, this AP is a destruction operator for the particle, okay. This is a destruction is standard, no, AP is destruction and A dagger is a creation. This is destruction, but B, this is a creation operator for antiparticle. So, A is particle and B is antiparticle. Okay. Now, please see the sign, there is a minus sign here and there is a plus sign here. Okay. And these prefactors I do not have time and I do not want to get into this. So, this is a space part, in the time part integral, well, this has come here, it is going to be, it has a connection with relativity, but we will not get to that. Okay. So, prefactor please ignore it and focus on the signs. So, Px in relativistic notation, this is 4 momentum and 4 time. So, it is written as Et minus P dot x. Okay, Px is written is like that, Et energy times time minus P dot x. So, energy is coming with a minus sign, right, there is a minus I there. So, this is the particle, see minus IET, I like that, no, I mean I wrote I p dot x minus IET, these are particles. I want to say, well, positive frequency particles with linear momentum positive will go in x direction. So, that is why this for particle. Here is a plus IPX, it has totally opposite interpretation. This guy will come with IET plus IET minus P dot x, okay, it is a positive energy, negative energy. So, that there is a no minus sign here, there is a minus sign here and there is a no minus sign here, and this is how we combine the two set of particles. Now, let us dig deeper, I mean it is sensible or not. I am not going to do all the algebra, but I will just show you where to look for in that in the book. You can prove it that A dagger P, okay. So, this is an operator. So, at time t equal to 0, we have A dagger P, not A dagger, AP operator AP, and this is operator at time t. How do I get this in Heisenberg picture? I put this evolution operators and dagger operator. No, this is how Heisenberg picture we evolve operator by this, and you can show that this equal to minus exponential minus I EPT. There is a minus sign sitting here, AP. This is there in this book, which QFT for gifted amateurs, example 11.1 is bit of algebra, but essentially we multiply this by you operate on a field of NP, NQ state, and then see what happens, and you will find that this prefactor will come out. So, this is looks nice that this corresponds to a positive energy particles, okay. So, so this looks like, well, I am not deriving it, but I am telling you this is a reasonable field operator for destruction operator for particles, particle and antiparticle together. Now, this is for creation operator phi, sorry, destruction operator phi, creation operator phi dagger. So, what do? The prefactor is a number, do not worry about it, but now I need to do the transpose, well, basically dagger operator on A, and I need to change the sign of this, right, complex conjugate and transpose. So, AP become A dagger P, and exponential minus IPX will become exponential IPX, and B dagger P will become BP, and this is become exponential with the opposite minus IPX, okay. So, we constructed, well, I am just stating what is the phi operator and phi dagger operator for Klein Gordon field.